Welcome, geniuses, to Just the Basics quiz, or quiz practice 4A. There'll be another video of 4B as well. And before we get started in here, something that we're probably pretty good by this stage at, just a little review. If we had this equal to 0 and we were going to solve it, we might be encouraged or tempted to factor a 2 and an x to the 4th out. And as we all know, we'd have 4x to the 3rd, but where did the 3 come from? That came from 7 minus the 4 of them we factored out, and then we would get a minus plain old 3. And we'd continue from there, ... Why am I showing you that? Because that's something we're very familiar with, but we're gonna actually utilize that in an environment we're not quite so familiar with. So we'll come back to that. All right. To find the derivative of this, I'm going to go ahead and think of this as 3 times quantity 2x squared plus 4 to the. We're going to write this as an exponent. Since it's in denominator, it needs to be negative, and the exponent for square root would be 1/2. And I'm going to use that. I would rather deal with this than this quotient rule. So first derivative, we might be thinking, well, now we have to product rule. If we did, we'd be taking 3 times the derivative of our mess here, plus derivative of 3 times the plain old mess, but the derivative of 3 is 0, so we don't have to do the second half of that. The 3 just goes along for the ride. So we get 3 times the derivative of this. The derivative of this is a chain rule, so outside derivative, negative 1/2 of something to the reduced by 1, subtract 1. Minus 2/2 would be negative 3/2. That's the mother derivative. Leave the baby alone. Treat the baby. Okay? Got a handful there, but we've certainly handled problems more difficult than that in preparation for this. So let's see. Monomial, monomial, monomial. 3 times 4, 12. X times a negative is negative 12 on 2x, or negative 6x, times 2x squared plus 4 to the negative 3/2. So there's our first derivative. I'm going to write that as negative 6x on 2x squared plus 4 to the positive 3/2. And if you want to write it to the third, the square root of, and then to the 3rd power, that's fine. So when this is 0, at 0, the slope is 0. Okay, that's our slope. First derivative, slope. The slope is 0. If I put a number bigger than 0 in here, like 3, I get negative 18 on a positive. Negative divided by positive, negative. If I put something smaller than 0, like negative 2, I get positive 12. The denominator is always going to be positive. Positive divided by positive, positive. Therefore, our graph goes up, levels off, and comes back down, giving us answers to, hey, we have a maximum. Goes up, comes down. We have a maximum. X coordinate of the maximum is at 0. And we are increasing when the slope is positive, negative infinity to 0. And we are decreasing when the slope is negative, 0 to infinity, and we don't have a minimum. So pretty tame compared to what we did on the last on JTB 3. All right, let's find the second derivative. Now for the second derivative, we do have to use product rule on this, or quotient rule on that. I'm going to stick with product rule. So we want the plain old first function times the derivative of the second. So that would be times treat the mama function, negative 3/2 something to the reduced by 1, negative 5/2, leave the baby alone, 2x squared plus 4, treat the baby, 4x. Wow, and it's really simple here because we did a lot of things here. It's simple. It would be very simple here just to move on. Oh, we got the second derivative, just simplify it. But all we've done so far is taken plain old first times derivative of second. Now we need to go plus derivative of first, negative 6, times plain old second, 2x squared plus 4 to the negative 3/2. All right, let's do a little bit of simplifying here. I've got a negative times negative positive. I've got 6 times 3, 18, divided by 2, 9, times 4, 36. I've got an x here and x there, x squared, 2x squared plus 4 to the negative 5/2. And I'll be honest, more people make mistakes in that step right there than doing the calculus itself. Got a plus negative, so minus 6 2x squared plus 4 to the negative 3/2. And there's our second derivative, but we need to get that in a more useful form. And I'm going to bring you back to right here. Factoring. I look at these things and clearly we could factor a 6 out. And they both have 2x squared plus 4's to give, just like these both had x's to give. How many did we take out? 4. 4 being the smaller number. Well, I've got negative 5/2 of these and negative 3/2 of these. I can factor out some of these. But which is the smaller number, negative 5/2 or negative 3/2? Negative 5/2 is actually smaller. So we're going to factor out negative 5/2 of those. What am I left with? 6 times what? I need a 6. I need an x squared. I've got the negative 5/2 of the 2x squared plus 4 factors, so minus. This would just be a 1. The 6 is out of there. All that's left is some 2x squared plus 4's. How many of those do we have left? Need an exponent there. Well, what did we do here? We took out the smaller number. I took out 4. I took 7 minus 4. We're taking out negative 5/2. I want to take negative 3/2 minus negative 5/2. And negative 3/2 minus negative 5/2 is plus positive is 2/2. Holy smokes, this is just a 1. Wow, is that nice? All right, a little bit of a leap here. Equals. I'm going to leave 6 in the numerator. I'm going to bring 2x squared plus 4 down to the denominator, make that to the 5/2, and I'm going to simplify this. So we get 6x squared minus 2x squared, 4x squared. This minus distributes minus 4, so I might want to think of that as factor out of 4, 24x squared minus 1 on 2x squared plus 4 to the 5/2. In fact, I might want to think of that as 24 times x plus 1, x minus 1. Factor this, difference of perfect squares, on bad x. 2x squared plus 4 to the 3/2. And we ask, when is this 0? This is 0 when x is negative 1 or 1. Second derivative, our concavity test, is 0 at plus or minus 1. Let's try something in between here, like 0. Put in 0, I get 24 times 1 times negative 1. That's a negative. Put in 2, I get 24 times a positive times a positive. That's positive. Put in negative 2, 24 times negative, that's a positive. Our graph cups up, cups down, cups up, giving us inflection points of at plus or minus 1. And concave up from negative infinity to negative 1. We're doing a pretty good job getting our union symbols in, almost everybody, in union with 1 to infinity, concave down, negative 1 to 1. And all that's left is the graph. And guys, we should be able to get the graph. That's been costly to a couple people that do the calculus part really well, but now we have to interpret. The whole purpose for us doing this is to be able to come up with a nice general look of what the graph is. So here's our function to begin with, 3 on square root of 2x squared plus 4. Let's find f of 0. f of 0 is 3 over 2 times 0 squared plus 4 square root of 4, or 2. Well, that's a nice convenient point right here. And now let's consider what the graph looks like at that point. Holy smokes, at 0, that's a maximum, and it's concave down, which kind of confirms that it's a maximum. Looks something like that up there. All right, let's consider f of, I'm going to go 10. I refer to it as being out of the fray. What's the fray? Well, the interesting things, calculus things that happen on this graph happen at 0, -1, and 1. So I want to get well beyond that. I'm going to go to 10. f of 10, put in 10, I get 3 over square root of 100 times 2, 204, which is positive, but barely. And as I put bigger numbers in for than 10, this number is going to get bigger and bigger and bigger. 3 divided by bigger and bigger and bigger. This is what I would refer to as it's trying to be 0 from the positive side, positive 0. It's getting sucked into 0 as x gets big. Guys, take a look at this. Don't ignore this part. If that's getting sucked into 0, it's cupping up and going down. Oh, okay, let's consider f of -10. f of -10, how convenient here. f of -10, we get 3 over -10 squared, 100, 204, square root of 204. And that starts to suggest, hey, we have an even function. Well, yeah, if we put positive or negative in for x, we get the same thing. So this is positive 3. This is trying to be positive 0 as we move to the left. So as we move to the left, we're getting sucked into 0. Let's take a look. That graph has positive slope and is cupping up. Positive slope, cupping up. And it continues to cup up until we get to -1. So somewhere in here, this graph goes from cupping down, not somewhere in here, but at 1, to starting to look like it's cupping up. And so this graph cups down in this direction until it gets here, and that's when it starts to make the turn and starts to look like it's cupping up. And there we have a really good representation of this graph. Maybe somewhat interesting to you. You might recognize this is what is often commonly referred to as a bell curve, or used in statistics, normal distribution. So there we have it. That's the first one. There's going to be one more example. It's going to be a little bit quicker. Good luck. Let us know what we can help you with.